This week, we have been doing calculation of electric and magnetic fields from a linear wire antenna and a magnetic dipole moment. Previous week, we did a calculation of fields, radiation fields from a point dipole. All this is connected with localized charge distributions. So, when these charges move, there are these currents. So, we have charge distribution as well as current distribution, which are time dependent. And we took special cases of point magnetic dipole and antennas. In this lecture, I want to look at it in a general way. So, therefore, it will sound a little repetitive, but I want you to go through this exercise of calculating the potentials for a localized charge distribution by expanding things. Then you will see all our previous derivations in a very consolidated way. So, what I am calculating now is the vector potential for a localized current distribution. The calculation for scalar potential goes in very similar manner, and that I leave as an exercise or assignment problem for you. So, what we are considering is a distribution of charges which are moving. And therefore, there is a charge distribution rho r t, and there is a current distribution J r t, and this is localized in a region which is near the origin, and we want to calculate the radiation fields from these distributions of charges and currents. And once we know that, we can calculate the power radiated and things like those from this. We have seen particular examples in the past, we are doing it in general now. So, as earlier, we are going to calculate the vector potential R t, which is given as mu 0 over 4 pi integration J r prime comma t retarded over r minus r prime d v prime, and the electrostatic or the scalar potential phi r t, which is given as 1 over 4 pi epsilon 0 integration of rho r prime comma t retarded divided by r minus r prime d v prime. I am going to focus on the calculation of vector potential. This is a little more difficult, and I will leave the calculation of scalar potential for you to do, because the expansions of retarded time in terms of r prime and r are pretty much the same. So, once I do vector potential, you can do the scalar potential very easily. And once we have these, you calculate the electric field as minus dA dt minus grad of phi, and the B field as curl of A, or in the radiation region it is also given as 1 over C r unit vector cross E. So, let us begin the calculation of the vector potential A r t, which is mu 0 over 4 pi integration j r prime t retarded over r minus r prime d v prime. And since the current distribution is localized, we will do the expansion of r minus r prime. So, let us do that. You have r minus r prime, which is equal to square root of r square plus r prime square minus 2 r dot r prime. There should not be a vector sign on r prime, and since this is localized, we have r prime mod is much less than r mod. So, we are going to keep only the linear term and approximate this r minus r prime as r minus n dot r prime, where n I am writing for the radial vector r, so that we can distinguish it easily. Otherwise, you keep writing r and r prime again and again, one gets a little confused. So, I am writing n for r, n for the normal vector. So, I have A r t equals mu 0 over 4 pi integration j r prime t retarded, which is t minus mod r minus r prime over C over r minus r prime dot n d v prime. Now, let us see what this t retarded is going to look like. T retarded is going to be t minus r minus n dot r prime over C, which is equal to t minus r over C plus n dot r prime over C. Therefore, I can write this quantity j r prime d r as equal to j r prime at time t minus r over C. You see, the r prime part has gone away from j in the time, plus j dot at r prime at time t minus r by C times n dot r prime over C, plus let me also write the second order term 1/2 j double dot r prime t minus r over C n dot r prime over C whole square, plus and so on. Then I have 1 over modulus r minus r prime as 1 over r minus r prime dot n, which by binomial theorem is going to be 1 over r 1 plus r prime dot n over r. So, this is 1 over r plus order 1 over r square term, which I am going to neglect. And therefore, I can write the expression for the vector potential A r t as mu 0 over 4 pi r integration j r prime t minus r over C d v prime plus mu 0 over 4 pi r integration j dot r prime t minus r over c over, there is nothing here, dv prime, plus if you like the j double dot term, but I am not considering it. So, I am dropping it right now. This would be enough to show what I want to show you. Let us now calculate these terms. So, what I have for you is that the vector potential A r t is equal to mu 0 over 4 pi r integration j r prime comma t minus r over c retarded time dv prime plus mu 0 over 4 pi r integration j dot at r prime t minus r over c dv prime. Let me call the first term one, let me call the second term 2 and calculate them one by one. So, term number 1 mu 0 over 4 pi r integration j r prime at t minus r over c dv prime. This kind of integral you have come across earlier when we were doing magnetostatics. Recall such an integral from your magnetostatics lectures. There we had shown that this integral is 0. Here it is not going to be 0 because j is time dependent. Let us see how it works out. So, let me write integral of divergence with respect to this primed variable of x I prime j at r prime t minus r over c dv prime, where x I prime denotes x, y or z for I equals 1, 2 or 3. So, this can be written as equal to unit vector in I direction. So, let me write this as x I dot j r prime t minus r over c integral dv prime plus integral x I prime divergence of j r prime t minus r over c. Keep in mind that the divergence is with respect to the primed variable. So, you get this equal to integral j ith component r prime t minus r over c dv prime plus integral x I prime, and divergence of j is the time derivative of density. Dv prime. So, the integral on top, one given here, I am now enclosing it, is equal to this integral out here. And for localized distributions, the integral on top is 0. this is 0 for localized distributions, and therefore, the right hand side must be 0. So, what do we get out of this exercise? I am going to write it in the next slide, but keep in mind, if you recall that integral from the lectures on magnetostatics, the second term here, this one which I am underlining, was 0 in magnetostatics. Now, it is not 0. So, what you have found now is that integral j ith component r prime t minus r over c dv prime plus integral x I prime minus d rho by dt, all evaluated at r prime and t minus r over c dv prime is equal to 0. And this gives you integral j I r prime t minus r over c is equal to integral d by dt I can take out. This is d by dt prime evaluated at t minus r c. I can correct that. I am calculating the time derivative with respect to this entire variable, x prime del rho over del t prime r prime t minus r over c. This is t prime calculated at t prime equals t minus r over c dv prime. And this you can easily see is nothing but integral of d by dt of p I, ith component of the dipole moment, calculated at time t equals t minus r over c. If you like, you can write this t prime here, t prime equals t minus r over c, same thing. So, what we have found, therefore, if you write the vector form now, that integral j r prime t minus r over c dv prime is equal to the time derivative of the dipole moment of the system at t prime equals t minus r over c, or p dot, that is what we have been calling it. So, first term gives me mu 0 over 4 pi r p dot, and this p dot is calculated at is d by dt prime p t prime equals t minus r by c. Next, we calculate the second term. This is a little more involved. This term is mu 0 over 4 pi r integral of n dot r prime j dot, this time derivative at r prime evaluated at t minus r over c dv prime, which I can write using summation convention as equal to mu 0 over 4 pi r n I, where n I is the ith component of n, integral x I prime j dot r prime t minus r over c dv prime. And I want to calculate this integral. And through this, I want to show you that this gives rise to magnetic dipole term and electric quadrupole term. We have seen in the past how magnetic dipole term gives out radiation. We have also seen how electric dipole term gives out radiation. So, this is coming all from this localized distribution. Quadrupole term I am not going to cover. Now, to calculate this, let us write the integral just like we did in the previous case of divergence with respect to primed variable of x I prime x j prime j dot r prime at this t minus r over c. dv prime. And you will see how we get this term from here. So, I am evaluating integral of divergence of x I prime, x j prime, j dot r prime, t minus r over c dv prime, and this is 0 because the current distribution is localized. But if I expand this, this comes out to be integral x j prime j dot ith component r prime evaluated at t minus r over c dv prime plus integral x I prime j dot at r prime t minus r over c dv prime plus integral x I prime x j prime divergence of j dot r prime t minus r over c dv prime. Remember what I am after? I am after integral x I j r prime t minus r over c dv prime x I prime. So, I can write from here integral x I prime j j dot, there is a dot also here, j j dot r prime at t minus r over c time dv prime is equal to minus integral x j prime j dot ith component r prime t minus r over c dv prime minus integral x I prime x j prime. I am again going to use the continuity equation and write divergence of j dot as d 2 rho over d t square evaluated at r prime t minus r over c with a minus sign in front dv prime. And therefore, the integration x I prime j dot jth term, let us say we are calculating the jth term r prime t minus r over c dv prime can be written as 1/2 x I prime j j minus x j prime j I all evaluated at r prime time t minus r over c dv prime plus 1/2 of integral x I prime x j prime rho double dot, where double dot gives the derivative at r prime evaluated at t minus r over c dv prime. So, let us write this. So, the second term that we have gotten is 1/2 x I prime j j minus x j prime j I understood where it is evaluated dv prime plus 1/2 x I prime x j prime rho double dot r prime evaluated at t minus r by c dv prime. This particular term I can write this as 1/2 integral epsilon I j k r prime cross j r prime t minus r over c kth term dv prime. There was an n I also here, there was an n I also here. This you see, this cross product is related to magnetic moment of the current. We have seen that in magnetostatics, and there is an N I here. And the second term here, which I am encircling by blue, is related to quadrupole moment of the charge distribution. I am not worrying about that. I just want to show you how from this localized charge distribution you get the point dipole, point magnetic dipole, and also quadrupole, but I am not dealing extensively with quadrupole radiation. So, neglecting that, I can write the second term as mu naught over 4 pi n I one half integral epsilon I j k r prime cross j r prime t minus r over c dv prime. This is the kth term. Let us look at this term n I epsilon I j k r prime cross j kth term. I can write this as epsilon k I j r prime cross j k n I, and further as epsilon j k I r prime cross j k n I, which is nothing but equal to the jth component of r prime cross j cross n unit vector, jth component. So, the second term, jth component that we are after, is nothing but, there is an r also, mu naught over 4 pi r 1 half integral r prime cross j r prime t minus r over c dv prime cross n jth vector, jth component. And therefore, in vector form, this term is nothing but, second term in vector, full vector is nothing but mu naught over 4 pi r 1 half r prime cross j r prime t minus r over c cross, again I am going to write this r unit vector, n and r unit vector are the same, which is equal to nothing but this is m, this is j dot. Correct that in the previous slides also, I have been missing this dot. So, this is m dot. So, this comes out to be equal to mu naught over 4 pi r m dot cross r plus the quadrupole terms. And therefore, this vector potential A that I was calculating comes out to be equal to the first term plus the second term. First term, if you recall, is equal to the dipole moment dot calculated at T minus R over C dot R over R 4 pi epsilon 0 plus m dot calculated at T minus R over C cross R mu naught over 4 pi R plus quadrupole terms. Make correction. The electric dipole term is not 1 over 4 pi epsilon 0, but again mu naught over 4 pi. So, the correct answer for the vector potential is mu naught over 4 pi r p dot calculated at T minus R over C dot r unit vector plus mu naught over 4 pi r m dot cross r unit vector plus quadrupole terms. So, what I have shown you is that through a localized charge distribution, the dipole moment, the magnetic dipole moment and higher orders automatically come out. To deal with it mathematically, a further exact manner requires even more terms. You need to expand 1 over r minus r prime in terms of spherical harmonics. We are not getting into that. Our purpose was to show that the vector potential arises from these localized current and charge distributions, and that we have shown. What I have not shown is the scalar potential. That you will do. Please work on it, because I am going to give that in your assignment. Calculation is quite easy, because the main thing in all these calculations you must have noticed is starting from the calculation of potentials for point dipole, point magnetic dipole and the antenna, that what we need to do is expand the retarded time in terms of the distance from the origin to the point where we are observing the radiation, and the extra term that comes from r dot r prime. Once you do that, the rest of the calculations are quite simple. You can perform all other calculations now, because we have already calculated fields for p dot and m dot. So, that part you can do yourself. I just wanted to show how from localized charge distributions these terms arise, and I think we have done that. So, what I would expect you to do is calculate the scalar potential. Phi r t. 2. Calculate the fields from E equals minus dA dt minus grad phi and B equals curl of A. I am giving this to you again, so that you get some practice of doing this calculus when you use retarded time. And number 3, this is again a repetition from my previous work, ratio of m magnitude to p magnitude and M man u dot to P man u dot for length scale L and time scale T. So, finally, I conclude the lecture. Finally, I conclude the lecture by saying that we have calculated the vector potential for a localized current distribution. And I should add and the associated charge distribution. And shown how electric dipole and magnetic dipole radiations arise from it. What we have not done is the electric quadrupole radiation. Thank you.